In this problem from CSIR NET December 2023, we are given the longest wavelength in Balmer spectrum of hydrogen atom is lambda h, and the longest wavelength in Balmer spectrum of deuterium atom is lambda d. We have to find this ratio lambda h minus lambda d divided by lambda h times 100. So let's do this. We know the formula for wavelength of hydrogen or hydrogen-like atoms for different spectra. 1 by lambda is equal to R infinity mu times Z square divided by ME times 1 by NF square minus 1 by NI square. Now NF is equal to 2 for Balmer spectrum. And it is said that the wavelength should be longest, which means we need the 1 by lambda to be least. 1 by lambda to be least. For longest wavelength, 1 by lambda is to be least. This implies 1 by Ni square must be maximum. And for this, Ni square must be minimum. And what are the possible values of Ni? Because NF is equal to 2, Ni can range from 3, 4, 5, 6, 7, etc. And the least value of it is 3. Therefore, for Ni square to be minimum, we need Ni to be equal to 3. So NF is equal to 2 because we are interested in Balmer spectrum, and Ni is equal to 3 because we need the longest wavelength. Actually, it is not necessary to calculate the value of NF or Ni in this problem, because NF and Ni are same for both deuterium and hydrogen. When we take the ratio Y is equal to lambda h minus lambda d divided by lambda h times 100. So when we take this ratio, whatever is common in lambda h and lambda d, they will get cancelled. So NF and Ni, NF value is decided by the spectrum. It is 2 for Balmer spectrum, and for longest wavelength Ni must be 3 also. So these will be same for hydrogen atom and also for deuterium, and they will get cancelled because common factors will get cancelled when we find this ratio lambda h minus lambda d divided by lambda h. And also in this expression R infinity, this is also same. It is Rydberg constant. It is also a common factor. Z is equal to 1 for both hydrogen and deuterium. Me, mass of electron, it is also same for both hydrogen and deuterium atoms. The only thing that is different here is mu. And lambda is inversely related to mu. Lambda is inversely proportional to mu. Therefore, we can write Y is equal to, instead of lambda h, we will write 1 by mu h. All the other factors will get cancelled because they are common in both deuterium and hydrogen wavelengths. And instead of lambda d, we will write 1 by mu d divided by 1 by mu h times 100. This is what we have to find. Now mu is the reduced mass. It is given by Me times Mn, where Mn is the mass of nucleus, divided by Me plus Mn. So Me times mass of electron times mass of nucleus. Mass of nucleus for hydrogen atom, it is 1 proton is at the nucleus, and 1 proton is approximately 1836 times mass of electron, divided by Me plus mass of nucleus. Mass of nucleus is 1836 mass of electron. Therefore, this is coming out to be equal to 1836 Me divided by 1837. Now 1 by mu h, if you take the inverse, you will get 1837 divided by 1836 Me. Now let us find the reduced mass of deuterium atom. In the case of deuterium, we have one proton and one neutron at the center in the nucleus, and one proton, mass of proton is approximately equal to mass of neutron, and mass of proton is approximately 1836 times mass of electron. Therefore, we have reduced mass of deuterium atom. This is equal to mass of electron plus 2 times 1836 mass of electron, because we have one proton and one neutron in the nucleus in the case of deuterium atom, divided by, here it is multiplication, divided by mass of electron plus 2 times 1836 mass of electron. This is how you find the reduced mass of deuterium. So you get 3672 mass of electron squared divided by 3673 mass of electron. From here we have 3672 divided by 3673 mass of electron. Now 1 by mu d, this is equal to 3673 by 3672 times mass of electron. Now let us find this ratio. Y is equal to 1 by mu h minus 1 by mu d divided by 1 by mu h. Y is equal to 1 by mu h is 1837 by 1836 ME. 1837 by 1836 times ME minus 1 by mu d is 3673 by 3672 ME. The whole divided by 1 by mu h, which is 1837 by 1836 times ME. ME gets cancelled from all the terms, and when you evaluate this, you will get this to be equal to 0.000272, and there is a 100 here, so you get this to be equal to 0.0272 percentage, and this is very close to option 3.